Hi, this is homework 4, part C1. We're going to be deriving the differential balance equations for concentration and temperature for an exothermic, continuously stirred um, tank reactor. So, to start, we can draw our reactor. So here we have a reactor, and we are going to have some temperature and some concentration. And for our system, we are going to have some flow in, and we are going to have some flow out at the top of our tank. So for our flow in, we are going to have a Q in, the concentration in, and we're also going to have some temperature in. And since our system is continuously stirred, it will be continuously steady state. And since it's coming off the top, it will also have some Q in for the same rate since it is coming off the top. And it'll also have the concentration, the same concentration and temperature. As it is going in, it'll come out the same since it is continuously stirred and due to it coming off the top. So for our tank reactor here, I'm going to draw some sort of temperature jacket just so that we know that could possibly be some change in temperature since we are looking to derive the differential balance equations for the temperature. So we went ahead and did that. So next we are going to want to look at the differential rate of change of our concentration with respect to time. And before we made it Q in minus Q out, so here we are going to make it the concentration in minus the concentration out, which is Ca, because it's perfectly stirred, it is the same. But here we are going to multiply by our Q. So we have Q times our change in concentration, which would most likely lead to be 0. And then this is going to be subtracted by some constant K for our heat of the jacket. So we have minus K, and then that is going to be multiplied by the concentration and the volume of our system. And on the left side here, we're also going to multiply this by volume, just due to our system volumes varying from the flow in and the flow out. So our next step here with this expression is going to be divide by the volume in order to cancel it out in these two pieces. So we can have the differential of our concentration over time is equal to Q over V times our Ca in minus Ca minus the K times Ca. So what we found here is our differential balance equation for the concentration and our continuously stirred tank reactor. So what we're going to do next is derive a differential balance equation for the temperature in this CSTR reaction. So to start here, we can go the differential temperature over time, and we can make that set equal to the temperature in minus the temperature out, which we label as Ti minus T. And we also know that we have some mass, so we're going to need to come up with a way to include mass because we have some mass in our system and we need to find the relative temperature related to it. So we're going to use our density expression, which is mass over volume, and we are rewriting that as mass is equal to the density times volume. So we are multiplying this expression by the density times volume, and then we are also going to multiply it by a constant c, because we need joules in our expression here, so we are going to just include it with this constant here. So on our right side here, after we have our temperature, we are going to again multiply it by our heat constant here, C. And then once we do that, we are going to want to multiply by our density and then times our Q value. We multiply by our density because we have a concentration, and we need to multiply by Q because we have some flow in the system. So after we do this, we are going to then add, as we did up here, our K for the heat jacket, the K times the concentration times the volume, and then here we are going to be multiplying by the negative heat loss of our reaction. Due to it being exothermic, it is negative. So once we have that, we need to now think about the heat loss from the energy that we are losing. So what we are going to do here is then subtract the temperature minus the temperature of the heating jacket here, and then so we have T minus TC, and then that is going to be multiplied by the heat transfer coefficient, U, and then multiplied by the area of contact of our system. So once we have this, we need to do some massaging to our balance equation in order to come up with it in terms of just our differential of temperature over time. So now we're going to rewrite this as just our dt, differential of temperature over time, and we're going to divide the right side of this by C times our density times the volume. So doing so, we'll cancel CP, so we will just have Ti minus T, and then this will be multiplied by Q over V, and then plus our K Ca times negative delta H of our reaction, and then over Cp, C times density, and then lastly we will have minus the temperature of our outflow minus the temperature of the jacket times our thermal heat coefficient times the area, and this will be all over C times density times volume. So what I've just derived here is the differential balance expression for the temperature of our exothermic continuously stirred tank reactor.
Hi, this is homework 4, part C2, and we're going to be numerically solving the initial value problems using scipy.integrate and solve_IVP, and we're going to be plotting the results for TC equals 290 and TC equals 305. And we will be also explaining the oscillatory behavior for 305 kelvins. So to start, we are going to go to Google Colaboratory. This is homework 4, part C2. And as we did in all of the other codings, we are going to import numpy as np, and we are going to go from scipy.integrate import solve underscore IVP from plotly.subplots import make subplots. So once we have our libraries imported, so we're going to want to look at this table. And I'm going to split this screen just to make it easier for us to look at. So we have Q is equal to 100, CAN is equal to 1, TN is equal to 350, V is equal to 100, rho is equal to 1000. Next we have C is equal to 0.239 joules per gram times kilogram. Now we have the negative change in the heat of our reaction, so we can write that as negative HR, and that is going to be equal to 5 times 10 raised to the 4th power joules per mole. Next we have E over R, and that is equal to 8750 kelvins. And then we have our K naught, and that is equal to 7.2 times 10 raised to the 10 power. Next we have our UA, which is our thermal energy heat coefficient, and that is equal to 5 times 10 raised to the 4th. And then we have TC is equal to 300 kelvins, CA naught is equal to 0.5 moles per liter, and then we have T naught is equal to 350 kelvins. So now that we have all of our initial conditions inputted into our code, I'm going to now input a time for our simulation to end, and I'm going to make that 10 minutes. Shift enter. Next, I'm going to define my differential equation with the differential of volume with respect to time. So we're going to go define dv dt, and we are going to make the variables for this time and volume. Next, we are going to declare our variables that we are looking for, and that is our concentration and temperature, and we are going to make that equal to our V, so that we can use those two functions that we are looking for and plug them into the same differential equation, just with different boundaries and such, in order to solve our problem at hand. So from our previous part, we have derived differential balance equations for concentration and temperature. So here we are going to include those derivations. We found that our KCA is equal to the concentration times our K naught value times NP dot exp, because we're using an exponent. We're raising it to the negative ER over T. Next, we are going to bring in our differential rate of change of our concentration with time into our code, so we can label that as dCA dt, and this is going to be equal to our concentration in minus the concentration that is leaving, and then that is going to be multiplied by Q divided by our volume, and then subtracted by our KCA, which was the constant times our concentration of the system. Next, we are going to input our rate of change of our temperature with time, and we can denote that as dtemp dt is equal to the temperature that was going in subtracted by the temperature out, and then that is also going to be multiplied by Q over V, and then we are adding the negative heat of the reaction, and that is again due to the thermal heat jacket of our system constantly trying to hold the temperature constant. That is then multiplied by the KCA and then divided by the density rho times our C. That is then subtracted, and then we are going to subtract the temperature minus the temperature from our cooling jacket, or temperature jacket, and then multiply by our thermal constant of heat constant, UA, and then divide by rho times C times V. And then we are going to want to return the two differential balance equations, and those are dCA dt, the change in concentration, and the change in temp with respect to time. Shift enter. Now we are going to bring in our solve IVP function from our scipy.integrate by we're setting vec is equal to solve underscore IVP, and our function here will be dV dt, change in volume with time, and our x is going to be, and the parameters for this is going to run from 0 to t end, and our initial values are going to be our CA naught and our T naught values. And then, as we did in the previous parts, we are going to make this a dense output is equal to true. And lastly, in this line, we are going to make our method equal to rad dow, and we are using this method because it makes our answers more accurate, and it just takes a little bit more time than the normal standard method. And now we are going to initiate our plot, so we can go tplot is equal to np.linspace, and our parameters are going to be the same as they have been in the previous codes, so we can just go 0 to our t end, and we can make this 500. Okay. So next we are going to go CA, our concentration T is equal to vec.sol, and we are using our tplot so we can put it into our values into our graph. Shift enter. Now we're going to go fig is equal to make subplots, and again we are solving for two different unknowns, and that is the concentration and temperature. So in order to plot the two all at once, we are going to need to initiate rows and columns into our code. So now we can go fig.add. We're adding a scatter. Our x is going to be the tplot values. Our y is going to equal the concentration, Ca. The name of this plot, this one is going to be our concentration. Mode is going to be equal to lines, and this is going to be row 1, column 1. Shift enter. Nope, I didn't mean to run that, because we still need to include our temperature plot. So I'm going to control V, control paste that, and I'm changing this name to temperature. Our Y is going to be T, and our column is going to be 2. Shift enter. So here is our two plots of our concentration and temperature. As you can see, as it is going down, it slowly starts to increase, and then it rapidly shoots up, and then it starts to reach a steady state and starts plateauing around the value of 9 towards 10. And our concentration, or for our temperature, you can see that it starts very high, and then it starts slowly decreasing, and then rapidly speeds up to a very low value. So after we have these two plots plotted, so now that we have these two graphs here, our next step is to change the temperature to 305 and see what we get. So we go to TC, we make it 305, shift enter, and we get an oscillatory graph for each of our concentration and temperature. And to explain this, we can determine that we are starting with a higher concentration, and starting at a higher concentration means that the reaction will go through quicker, like it'll take less time to run. So as we're starting to go up, it starts to like slowly go down until it goes very low, and when the concentration is low, the time of the reaction is slowing down. But as that is happening, we notice that the temperature is rapidly increasing, and we also notice that there's peaks around 2.5, and right here it's around 2.4. So, and going to the next one around 4.7, it's around 4.6, 4.7. So we can go ahead and determine that these two plots are sort of like inverses of each other. So as we're starting at a high concentration going down, we are starting at a low temperature and rapidly going up, which is creating this oscillatory function that we have here. That is all for this video. Thank you.